Now we know all the basics about the binary genetic algorithm, and then so we would like to ask one question: why do GAs work? And then so we are going to turn to the schema theorem. Yeah. So this schema theorem that is given right here, summarized by this box. And then so now we only consider the binary genetic algorithm. And then it mentions that short, low order, above as average schemata receive exponentially increasing trials in subsequent generation of a genetic algorithm. So we have to understand word by word to understand what it means. And then later on, I'm going to define short. I'm going to define low order, above average schematas. And then now it means that for certain chromosome in the population, it means it will increase the number of itself or copy of itself, that is the offspring in the subsequent generation. It means that the better the quality of the chromosome, it will have a higher chance to be reproduced and survive to the next iteration, and the number will be growing as well. Yeah, so this is the survival of the fittest. Each iteration it improves the performance later and later, and then there will be more copies and more copies, and also the performance will be improved. So we want to so about this. Yeah. Okay, and now the first thing we need to know, that is, what is a schema? Because when we talk about schema, actually a schema, that is a template that represents the binary string using symbols. That means when we talk about a binary string, actually we are talking about the chromosome, because the chromosome that is represented by binary string. We know that the binary string represented by 0 or 1. Now I'm going to introduce the star. This star symbol, it means that it is a don't care symbol. It means it can represent 0 or 1. For example, schema star 1100 matches 2 string, because this one can be 0, this one can be 1 as well. So we have these two possibilities. When star takes the value of 0, so we have 0, 1, 1, 0, 0, that is the first string, binary string. And then the next one, the first bit, we place the star by 1, and all the rest, they are the same. Okay, so 2 string, and then if we are going to have 2 star, we have 4 combinations, because this one can be 1 or 0, this one can be 0 or 1. So we will have 4 combination. Yeah, 0, 0, 1, 1 for the first star, and then the last one will be 0, 1, 0, 1. So this schema represents 4 string. If we are going to have all star, because each star will have 2 possibilities, so in total 5 bits, we have 2 to the 5 string. Yeah, from all 0 to all 1. If we ask the question reversely, that means how many schemas matches this string 11100? We only have 1 schema. That means schema, we do not need to have a star. Yeah, so that means this binary string itself is a schema as well. Yeah. So if we are going to ask a question that 11100 is matched by how many schemata, and then we will have 2 to the power 5. Yeah, so that means 11100 itself, and also we put a star right here, and then shift the star into different position. We are going to use multiple star, and then you can just simply play around with this. You will know how many schemata we have for one single string. Okay, this is the schema, and then now we are going to talk a little bit more about the property. When we talk about a schema S, yeah, so this S, that is, for example, star 1100, that is what we mentioned before. When we talk about the order, that is the number of the fixed position. That is, when we talk about the fixed position, that is about the bit 0, 1, we're not talking about the don't care symbol. Now take a look at this as an example. When we talk about the schema 1, star 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 001 star 110. And then when we talk about the order, that is 6, because the number of fixed position, that is 1, 2, 3, 4, 5, 6. That means we are going to count the number of 0 or 1 in this binary string. So in total 6. Second schema, 1, 2, 3 fixed position. So this order, that is 3. Schema 3, 1, 2, 3, 4, 5, 6, 7, 8. The order, that is 8. Yeah. Okay. Now this is the order. Now we are talking about the length of a schema. S1. Okay. So schema, the length of a schema, that is the distance between the first and the last fixed position. So when we are talking about S1, okay. So the difference between the first and the last position, and then this is the first position, this is the last fixed position, because this one we have a 0 right here, not star. This is the first position of the binary bit, that is a fixed value, not a star. So we are going to count the position. This is position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The last position, that is right here. So we have 10 minus 4, that is the position of this 0. 10 minus 4, that is 6. We are going to do the same for the rest. For example, this one, this is the position 1, this is the position 10. 10 minus 1, the length of this schema, that is line. Yeah. Now we define what is a schema as well as the order and the length, and then we go back to this one. When we talk about the short schema, that means that is the length we define right here. The second schema, S2, that is shorter than S1, and S1, that is shorter than S3. Yeah. When we talk about a lower order, it means that is, say, this order, that is lower than 6. 6, that is lower than 8. So that means when we compare the length and the order, we know which one is shorter. We know which one the order is lower. Yeah. Okay. And now we are going to look into details about the schema theorem. And then before we are going to develop this theorem, we are going to define the configuration of the binary genetic algorithm. And note that if you are going to use different configuration of the binary genetic algorithm, we will come up with different result or different outcome for this schema. So this one, the binary genetic algorithm, actually we are going to, for example, we have a population that is t minus 1, that is the previous population, and then when we enter this process, we are going to generate the current population, for example, right here, pt. So right here, we are going to do something so that we will generate the intermediate pt, and then we are going to do the genetic operations right here, crossover, mutation, and then come up with the final population for this current iteration, and then evaluate the cost of this chromosome, rank the cost, and then go back to the top and increase the value of t. This is the process we have right here. And now we are going to look at a little bit details. When we talk about this schema theorem, we set n cap to be 0. That means when n cap, that is 0, we are going to generate the whole population using the parents. Yeah. Okay. The selection process, that is the cost weighting, and then the crossover, we are going to use single point crossover. That means we only allow one point to perform the swapping, and then if we are actually we can extend it to any kind of crossover. Again, if you are going to change the configuration, we have to change accordingly to develop the schema theorem. Mutation, uniform mutation, that means each bit will have the probability of PM to be flipped from 1 to 0 or 0 to 1. Elitism is not implemented. Okay. Now, that is what we are going to do. Assume that we have a population. this population size and pop, that is 6. Okay, so this is the population at the generation T, and each bit, the length of the chromosome, that is 6. And then so before we are going to go further, make sure that we are going to normalize the cost. So this column, that is, we assume that we have normalized the cost so that all of the cost, they have the same sign at the moment, that is all negative. Yeah, but now this is the what we are going to do now, that is, we are going to do the cost weighting, so that we are going to calculate the probability that each chromosome to be selected, that is according to this probability. Minus 15, that is its cost. And then so this f of t, that is the total sum of this column. So we are going to compute the probability that we want to be chosen as parent. That is exactly the same what we have done in the cost weighting. Yeah. Okay. The second, the third, and then calculate each one of them. Yeah. And now, you can just find out that right here the cost, that is not rank. So I would suggest that we are going to rank the cost so that we can see the picture clearer. But if we are not going to rank it, it is fine, yeah, because we do not have the lateral selection for this one. But anyway, as I suggest, it is better to rank the population. Anyway, after we have this probability table, what we are going to do is just to select the parent, yeah, because we need to do crossover and mutation. So that means according to this probability, okay, we are going to select the first parent, this parent, V1 prime. Note that this V1 prime, that is not this one. Yeah, so this is just a symbol to represent that I'm going to generate a random number. Choose one of this V1 to V6 according to this probability to be the first parent, and then we do the same for the second parent, so and so. Yeah. Okay, we require to have 6 because we are going to pair them up so that each pair will generate 2 offspring, and the offspring and the 6 offspring will replace the whole population. Yeah, so that is why we call this is n kept equals 0. We are not going to keep any one of them. We just use the offspring to replace the whole population. So the next step, that is to perform crossover. Yeah, so that means each pair of V1, V2 prime, yeah, because yeah, and then they are going to perform crossover. The second pair, they are going to perform crossover, and then the third pair performs the crossover. After the crossover, and then so we are going to do mutation, yeah, mutation on O1C, so and so, yeah, according to the probability of mutation rate we are going to choose. Yeah, so that is the picture about the configuration of the binary genetic algorithm. And now once we define the configuration of the binary genetic algorithm, and then we know what the order it is, the length of the schema it is, and then we are going to define another variable. We call this ZST. See, right here, it means that we are talking about the number of the strings in the population. That population, that is at the generation T, that is in the iteration T, and then the number of string that match, yeah, the number of string that matches the schema S right here. For example, we have a population right here. Again, please be reminded that this cost is normalized. Yeah, they are normalized so that they are all negative. And then we would like to ask a question that what would be the number of string in this population matches S1 in this iteration T? Okay, the answer, that is 3. Why it is 3? We are going to check this schema. Star, 0, 1, star. So we are going to check whether we want to satisfy this schema. Okay, so we are going to, because this is star, the first bit, that is star, so we don't care about what value these 2 bits are. So this in the middle, this is 0, 1. So this schema, that is S1. And then for this one, that is not 0, 1. So this is not S1. And then V3, we have 0, 1 again. So this match the schema S1. And then V4, we have 0, 1 in the middle. This is S1. This one, that is not 0, 1. This one, that is not 0, 1. So in total, we have 1 S1, 2 S1, 3 S1. So in this population, in this current iteration T, the Z, the number of string that matches S1, that is 3. Okay. Now, we are going to define another variable, lowercase fst. It means that this is the average cost of all string in the population matched by the schema S. That means we are going to find out the schema S in the population and their average cost F. Okay, now this is the equation. P, that is the number of string matches this schema S, and then U1 up to UP, that is the string in this population that matches the schema S. Now take a look at this example so that we understand how do we apply this equation. The numerator, that is the sum of all the costs corresponding to those string matches the schema S, and then P, that is the total number of the schema matches S. Now when we talk about S1, just consider the same schema, and then we know that from the previous slide we have V1, V3, V4 satisfy this schema S1, and then I just listed right here, and then so now we are going to calculate the average cost of this schema S1 in this population at the iteration T. So expand this equation. So we know that P, that is 3, because we have 3 schema matches this S1. So the first one, that is V1, that is this guy. The second one, that is V3. The third one, that is V4. The cost of V1 according to this population, that is minus 15. So I'm going to put minus 15 right here. Cost of V3 and V4, that is right here. So minus 6 minus 1 divided by 3, minus 7.3333. That is the average cost of S1, this schema in this population, yeah, at the current at the iteration T. Now I'm going to define the objective. That is what we would like to investigate. This text box just summarized the objective. That is, we would like to investigate the probability of the survival of all the schemata S. This schemata S, that is from all 0, 0, 0 to all star. Yeah. So in between we have all 1 as well. So that means when we are given a schema, and then we would like to know that whether this schema will survive to the next iteration. Yeah. So that is what we would like to do, and then so we are going to investigate whether this schema will survive after the selection, whether it will survive after the crossover, and then after the mutation. Yeah, just one by one. And now, just to recall that this PI, that is the probability selecting the string VI as a parent. Yeah, so this is this equation that is not new to us. That is we are going to calculate the probability table, and then F right here, that is the total cost of all the chromosome. Yeah, so I'm going to give you an example later on, and then so now this ZST, again, this is the number of string matched by the schema S at iteration T in the population, and then so we also we are going to define this F lowercase f divided by F uppercase F. The meaning of this is the average probability of a string matched by schema to be selected. Note that this lowercase fst, it means that that is the average cost of a schema S at the iteration t in the population, and then this is the total cost. Yeah, okay. And the total number of string to be reproduced as offspring, that is n pop, because we are going to replace the whole population. Yeah, okay. This is I'm trying to explain what I just mentioned. Now this is the population we have. After normalizations, all the cost will be at the same sign, and then this is the equation I just mentioned. This is just the pi, that is this equation. Note that this f is different from this f. This f, that is without t, it means that this is the cost. Yeah, so this is the cost of x we used before. This is the cost function, fit as function, or the objective function. This fs comma t, the meaning is different. It is the average cost of s at the iteration t. That is what I have explained right here. Yeah, okay. Now this is the pi, or this is the p1. That is minus 15 divided by the total cost right here. So that is the probability we want to be chosen as parent. Yeah, okay. Now, according to this information we have done before, and then to S1, that is this guy, and then to matched by this 3 chromosome in this population, and then when we talk about S1Z, S1, that is 3, yeah, because we have 3 chromosomes right here, matches S1. The average cost of F for the schema S1 at iteration T, that is this equation we encountered before, that is minus 7.3333. Okay, now we are going to look at the meaning of this equation, of this expression, that is this one. Okay. So this one, because the meaning is that because this is it matrix S1, it matrix S1, S1 as well. So that means when we talk about lowercase f S1t divided by capital letter Ft, that is the probability of the schema S1 to be chosen as a parent right here. Yeah, okay. Now I'm going to multiply this CS1T to this guy. That is the probability. For example, the first parent to be any of these 3 guys. Okay. Again, right here, that's the meaning of this, that is any one of this guy to be chosen. And now the meaning of this one, that is in the parent one, the probability that it will be S1, that is one of them. Okay. And now when we move forward, because we have to generate 6 chromosomes right here, because the population size n pop right here, that is 6. So now I'm going to multiply this guy with n pop. The meaning is that because the physical meaning for this one, that is in each parent right here, the probability that it is S1, because we have to draw 6 times to produce 6 chromosomes. So that means the meaning of this one, that is in this new population here, the number of strings matches S1, that would be this number. Yeah. Okay. Now again, this is the probability that any one of the curve of the parent, that would be S1. And then now the population size, that is n pop. N pop times this one, that will be the FH number of string in this population. That would be S1. Okay. We understand that after the selection process, at this point, the number of string that matches S1 in this population, that is this value, that is the number of S1 in this string, in this population. Yeah. And now, if we are not going to do crossover, we are not going to do mutation, and just repeat this process. Yeah, repeat the GA process, and then we would like to know how this S is going to, what this S is going to do. Will it be increasing or decreasing? Yeah. So t plus 1 right here, that means in the next iteration, we would like to find out the number of string that matches S. Yeah. Okay. Because we assume that we stop at this point, we do not do crossover and mutation, and then so we just repeat this process, and then so we will come up something like that. Yeah. So the number of Z that is governed by this equation, and then now what I'm going to do is just to consider this n pop and f, and then write in as f bar t. The meaning is the FH cost of the population, because f, that capital letter F, that is the total cost, divided by the population size, and then it becomes the FH cost of the population. So now I'm going to put it right here, and then in the numerator we are going to plus f bar minus f bar. So this equation is exactly the same as this one, but what I'm going to do is just to define epsilon like this, that is the lowercase f minus uppercase f bar divided by f bar. Again, this f, that is the FH cost of the schema S in the population. Yeah. Okay. Now we are going to simplify this expression in the last equation, and we are going to look at actually what it means by this. Yeah. So now the last equation, this is the last equation right here. I just copy it into this slide. So we are going to use this is a difference equation, because on the left hand side that is t plus 1, on the right hand side that is t. So I'm going to just do this step by step, so that we are going to work backward, so that this t will become the first iteration. And now what I'm going to do is that look at this C as t according to this equation. If this one, that is t, and then this t should be t minus 1, this t should be t minus 1. So we have C as t minus 1 times 1 plus epsilon t minus 1. So I'm going to replace this bit by the right hand side. So everything becomes t minus 1. Yeah. And then we repeat this process. When this t plus 1 becomes t minus 2, t minus 1, and then this one will be t minus 2. So we come up with this. And then we repeat this process until we obtain z as 1. So you will just find out that we only have one term, that is c, all the rest in terms of epsilon at t equals 1, 2, up to epsilon t. Okay, just go back to the previous slide. This is the definition of the slide. That is f minus lowercase f minus capital letter F bar divided by the uppercase F bar. Okay, so I come up with this conclusion. When epsilon t, that is greater than 0, yeah, for most of the t, for example, all this epsilon, they are positive. Okay, and then I come up with the conclusion, that is, the number of s in the next iteration, that is increasing. Yeah. Okay. If all this epsilon t or most of them, that is less than 0, and then so these term, the number of s in the in t plus 1, that is less than the current iteration. Yeah, the number of string s, that is decreasing. Okay, so why it happens like that? Mathematically, for example, epsilon, that is greater than 1, so we have 1.1, this is 1.2. Yeah, 1 coming from this one, epsilon 2, that is 0.2, this is 1.1, whatever. So if you have something larger than 1, multiply them together, and this number will be greater than 1. Greater than 1. So when this is greater than 1, that means on the left hand side, this one will be more than this z as 1. Okay, now what happens if epsilon t, that is less than 0? For example, now this is 0.9, this is 0.8, and then 0.3, so and so. Multiply them together, everything is less than 1. So this one will be less than 1. So something less than 1 times c, and then this value will be less than this c as 1. So that's why in the next iteration, the number of s is reducing in the population. Yeah. So what is the meaning of epsilon t greater than 0 or less than 0? Just go back to this one. When f, that is less than this value, that means the cost. That is not as good as this one. Yeah. Okay. So that means. Okay. Just look at the example. When we talk about S1, that is star star 0 1 star star. Okay. F S1 t, that is minus 7.333 according to what we have right here. Yeah. Okay. Now f bar, that would be the sum of this one, that is f minus 55 divided by 6, that is this n pop. So both of them, they are negative. Remember that we are doing minimization. Yeah. So we will have, according to this equation, we will have minus 7.3333 minus 55 divided by 6, and then divided by minus 55 divided by 6. Now when we calculate this number, that is minus 9.1667. When you compare minus 7.3 with this minus 9.1, and then so because we are doing minimization, that means in the average cost in the population, that is better than the average cost of S1. Yeah. So in that case, if you're going to plug it into this equation, you will just find out that this will give you minus 0.2. Epsilon, if it is minus, it means that this S, that is below average. Yeah, that is below the average cost of the population. In that case, according to what we have right here, that is this S, I mean S1 is reducing in the next iteration. If we repeat this process, iteration by iteration, this S1 is going to die down. Yeah. Now we know that at this stage, we know how many string matching S will survive right here. And then now we are going to move on to the crossover. That means after we do the crossover, and then how many string matching S1 or matching S will stay in the population. So we define this as the probability of destruction of a schema. So we have delta S and then n bit divided by n bit minus 1. So you know, this is the order of the chromosome or the order of the schema. That is the number of fixed position. Yeah. So according to this equation, if we are going to consider S1 the fixed, because the delta right here, that is 10 minus 1. Yeah. So delta S1, that is line, because this is the first position, this is the 10th position. 10 minus 1, that is line. So this line that is coming from here. N bit, we have 10 bits right here. So 10 minus 1, that is line. It just tells you that if we are going to have this schema at this point to perform crossover, or right here to as the parent to perform crossover, 100% this S1 will be destroyed. And then the probability of survival, this PS1 minus the probability of destruction, that is the survival probability, that is 0. Yeah. Now when we consider this one SA, and then so 1, 2, 3, 4, this is the 4th position, 5, 6. So 6 minus 2, that is this delta. Yes, so delta SA, that is 2. Again, the number of bit minus 1, that is line. So probability of destruction, that is 2 over line, and then probability of survival, that is 7 over line. It means that it has a high chance of survival than destruction. Yeah. Okay. SB, again, we just use the same concept, come up with this probability of destruction and probability of survival. If we are going to consider all start right here, and then so because this the length right here, that is the order right here, that is 0. That means the probability of destruction is 0 and survival, that is 1. Okay. Now once we come up with this concept, probability of destruction as well as survival, we are going to consider these two particular cases to examine or to look at the situation why this lower order or okay. For this one, delta, that is the length, yeah. So that is not the order, yeah. So I'm going to correct this. And why this some of the short chromosome or schema will have a high chance to survive, yeah. Take a look at this example. Assume that at this point we want the parent V2 prime, that is these two guys. Okay, so assume that we are going to perform crossover once we choose these two as the parents, and then so we are going to say draw a line right here. This is the crossover point. Yeah, so we are going to draw a line right here. This is the crossover point. So we come up with the offspring O1C, O2C. That is, we generate these two offspring. Now in this case, you will just find out that V1 prime, we have V1 right here. Actually, this is SA. At the same time, when you look at these two bit 1, 1 and 1, 0, that is SB as well. So that means when we talk about V1 prime, that is SA and SB. Okay. Now, after the crossover, if we are going to choose the crossover point right here, and then we just find out that this one will be SA, and then this one will be nothing. Okay, another schema. So SA survives, but not SB. So it also mentioned right here that SA has a higher chance to be stay rather than compare with SB. Let's take a look at another situation. If we are going to choose the crossover point right here, and then so we are going to do the swap after the crossover point. And the offspring 2, we will just find out that this is SA, and then SA has a higher chance than SB. Yeah, so it also proves that when for a shorter chromosome, it has a higher chance to stay. And now we consider another crossover point that is somewhere right here. That is right here. That is here as well. And then both SA and SB cannot survive because these two offspring does not match SA and SB. That means SA has a higher chance to stay or to survive, but it also has some probability to be destroyed. Okay, and now if we are going to choose another crossover point right here, we destroy SA and SB as well. So we just looked at if we are going to choose the crossover point in between these 3 bits, we will destroy it. Yeah. Okay. Subject to the assumption that V2 that is not SA and SB. Okay. So this assumption also gives you the approximation of the probability of survival of this schema. Now, PS, that is 1 minus delta S divided by n bit minus 1, and then so because we assume that V1 prime and V2 prime, they do not belong to the same schema for simplicity. Yeah, if we are going to consider they could be the same, the process would be very complicated. So we make an assumption that V1 prime and V2 prime, they are not the same schema. So we are going to change the equal sign to greater than or minus, yeah, because when V1 and V2 prime, they are the same, and then the probability of survival will be higher, yeah. Okay, and now previously after the selection, this is the number of S in the population right here after the selection, and then we perform the crossover. The number of string times the probability of survival after crossover, and then that would be the number of S at this point. Okay, and now we are going to move forward, perform the mutation, and then to see how many string will stay here after performing the mutation. Okay, now uniform mutation, that means each bit will have a probability to mutate, that is to change from 1 to 0. For example, we are going to have a chromosome that is 0, 1, 0, 1, 0, 1. So for each bit in the population, we are going to generate a random number. If it is smaller than PM, we are going to flip this bit to 1. And then move to the next bit and then to generate. And R, if it is less than PM, flip the bit. If it is not, keep it to be 1. For example, this one that is R that is greater than PM, for example. Yeah. So that means each bit, each single bit right here, the probability of survival, that is 1 minus PM, because when the random number that is less than PM, we will flip the bit. When we flip the bit, we destroy the schema. Yeah. Now that means no mutation. This is the probability that this bit does not have mutation to take place. Okay. Now that is when we talk about the probability of survival of this S, and then so we will come up with this one, 1 minus PM, that is the bit we are going to flip. And then order of S, that is the order of S. That is the number of fixed position. For example, if we have star, star, 0, 1, star, star, the order of this S, that would be 2, just to recall what we have done before. Yeah. So because if it is a star, no matter whether we are going to perform mutation or not, it will become star, because star means 1 or 0. Yeah, so we don't care about whether we do mutation at this position. We just care about the fixed position. So that's why the probability of the survival of this schema S in this particular form, which will be this, yeah, 1 minus PM to the power 2. So that means we only care about this one. So now we put things together, and then now this one, that is the number of string right here after selection which match S, and then multiply this term, that is the probability, that is the number of S, in this population after crossover, and then the whole thing right here, that is the number of S right here that match the schema S. Yeah, the number of string S right here. Okay, so just go back to the schema. You will just find out that when the length of the schema, that is short, that means this number is smaller. So when this number is smaller, the whole term right here, it becomes greater. Lower order, it means that when this number is smaller, when OS, that is smaller, the value right here, that it will become bigger. And then above FH schema, that means when F, that is higher than F bar, and then that means that is about FH. In that case, this value will become more than 1, will be larger than 1. When all these three numbers, they are larger, it means that this value will become larger. So it just explains that why a shorter low order above FH schemata, they will receive exponentially increasing trials. In the next iteration, it becomes more and more. It is mainly because of this equation. Okay, now again, this equation, this theorem applies to the binary genetic algorithm subject to the configuration I mentioned right here or at the beginning. If you are going to change the configuration of the binary genetic algorithm, this equation does not apply, and then you have to redevelop that again. For example, if you are going to change the single crossover to double crossover, or you are going to change the cross weighting to any other kind of selection method, yeah,